This is just some information on ideal gases for those who might not have as much experience. I'm not going to go through this in detail, but ideal gases are idealizations, and no real gases are really ideal, but most gases are ideal if they are at low densities. We often call these dilute gases. There's an ideal gas law, PV equals nKT. P is pressure, V is volume, N is the number of molecules, K is the Boltzmann constant, and T is the temperature measured in absolute units like kelvins. The One of the things we often talk about are STP conditions, or sometimes just standard conditions. That means 1 atmosphere of pressure and 0 degrees Celsius. So the thing is that at standard conditions, 1 mole of any gas occupies 22.4 liters, and a mole is 6.02 times 10 to the 23rd particles. We call that the Avogadro number. And using the Avogadro number and multiplying it by the Boltzmann constant, we come up with the molar gas constant. And with it, we can actually then come up with an alternate version of the ideal gas law, which uses the number of moles instead of the number of particles. So the ideal gas law also contains Avogadro's law, Boyle's law, and the law of Charles, or the law of Gay-Lussac. It's the same law. Now let's look at some examples. If you look at a cylinder fitted with a piston, you can compress the gas, and I give some starting conditions and just work out what the change in pressure will be given the other changes in conditions. The important thing to note here is that we can take the ideal gas law, PV equals nKT, and we can rewrite it in the form that PV over T is equal to a constant. That enables us to write that the product of pressure with volume divided by temperature evaluated at any time is equal to the same term evaluated at any other time. And so we get an equation which allows us to make those sorts of calculations, and there's a simple illustration. Also, I go ahead and calculate the conditions for a mole of ideal gas at under standard conditions, and you'll notice that if you use the three significant figure data, you actually get 22.5 liters rather than 22.4. But if you go in and use the gas constant with more significant figures, and you use the standard atmosphere at with more significant figures, you actually then get 22.4 liters. So that's all there is to that sort of calculation. And I also go through and work a mean free path calculation, which you can look at. The bottom line is cut off in this particular shot, but you can actually download a PDF of this set of handwritten notes. So this is just some extra examples if you haven't seen very much of this before.